Hello everyone. So today I will be presenting the Generative Hypergraph Neural Network for multi-view brain connectivity fusion. Starting with the motivation, we are trying to answer three whys. The first why is why a hypergraph. Let's start by looking at this brain network represented with a graph. This representation is very simplistic as the graph is only able to model the pairwise interactions between regions. This will lead us to use the hypergraph, which is a set of hyperedges and nodes where a hyperedge can connect more than two nodes, and therefore it's more suitable to represent the brain networks. The second why is why hypergraph neural network. So the graph structured data are usually processed using graph neural networks, or what we call GNNs. The GNNs are a subtype of geometric deep learning models, and they are actually powerful to process non-Euclidean data. But when it comes to hypergraph, they are actually limited, and this will lead us to use the hypergraph neural network in our study. The third why, which is the most important, why generative hypergraph neural network. There are actually several studies that use the hypergraph neural network in their applications, but they are mostly focused on classification, prediction tasks, and in our work we are pioneering the generative aspect of hypergraph neural network. So the question that comes next to the mind, what are we generating? So we're using hypergraph neural network, the high order brain networks, to generate what exactly? Before answering this question, let's first try to define another new concept related to our work, which is the connectional brain template, which is an integrated graph that normalizes low-order brain network. So given this set of subjects represented with the brain networks, we try to integrate them together in order to get a population fingerprint, or what we call CBT. This CBT has many applications, such as comparing between typical and atypical populations. It can be used for supergraph resolutions, etc. So coming back to our question, what are we generating? So the main idea here is to leverage this CBT to the high order level. So using a set of high order multi-view brain networks, we will try to generate a hyper-connectional brain template. The main challenge here is how to fuse all these high order networks together in order to get a well-centered template. In order to achieve this, we propose the Gen-HNN, which is a deep architecture that generates a well-centered HCBT, and it captures the high-order interactions between brain regions. We also introduced a novel loss function that evaluates the representativeness of the generated HCBT. Our model is composed of four components. The first one is the hyperconnectome construction. So the starting point is a subject represented with a multi-view brain networks, where each view can depict a specific cortical attribute such as cortical thickness. We try to compute the corresponding hypergraphs for each one of these views using the k-nearest neighbor. And once the hypergraphs are computed, we concatenate them together in order to get a subject-specific hyperconnectome. Converted to a normalized hypergraph connectivity matrix that will be fed along with the input features to the hypergraph neural network, which is composed of two convolutional layers separated by a ReLU activation function. And then we get the subject-specific nodes embedding that will be used to generate the initial HCBT. We want for this HCBT to be well-centered and representative, so we evaluated against a randomly sampled subset R from the training set. For that, we introduced the loss function that calculates the Frobenius distance between the generated HCBT and the different hypergraphs in the random set. However, at this stage, we can still get a biased output. This is why we are proposing a post-training step. Specifically, once the model is trained, we input all the training subjects to get their corresponding HCBTs, and then we apply an element-wise median to get the final HCBT. Moving to the experiments, we used an NC-ASD dataset for our study. We empirically set all the hyperparameters using grid search paradigm And we trained for different models to generate the HCBTs for both hemispheres of two populations, NC, the normal controls, and ASD, the autistic subjects. And we also compared our model against recent methods, DGN and SNF. So to evaluate the generated template, we evaluated on 3 levels. First, for representativeness, we used the Frobenius distance that calculates the distance between the final HCBT and the different hypergraphs in a testing set T. So the experiments were computed on the left hemisphere. The results of our model, shown in blue, show the significant outperformance of our model compared to DGN and SNF, where it achieves the smallest distances. This shows its capability to represent the hypergraph structure. We also conducted the results on the right hemisphere, and we obtained the same trend. The second evaluation is the discriminativeness test. We used a one-shot learning approach. Specifically, we trained an SVM classifier using only 2 HCBTs for populations ASD and NC independently, and the performance metrics are reported in this table for the left hemisphere, where our model achieved higher accuracy values compared to SNF and DGN, and it also shows a more stable profile when it comes to identify the positive and negative cases. Finally, we identified the most discriminative error-wise. Specifically, we computed the absolute difference between the HCBT of ASD and the HCBT of NC populations for both hemispheres, and the results are reported in this circular graph, where we were able not only to identify the pairwise connections, but also the hyperconnections that most effectively differentiate ASD from NC. So to conclude, we proposed the first ever generative hypergraph neural network that generates HCBT that captures high order interactions in brain regions. Our model had superior performance in both representativeness and discriminative power, and also it's generic and can be extended to other network types. For future work, we will try to explore its application to functional and structural brain networks to get a more holistic templates, and we also will try to integrate more advanced regularization techniques to improve the generalizability of our model. Thank you.